Okay. Right. So we're going to be talking about the comparison of rates in SPSS. And for this particular lesson, we're going to be using the resident doctors 10 years data set. So if you go to Google Classroom, this should have been added sometime yesterday. Yep. So this 10-year follow-up data, you can go here and download the data set rds10y.csv. Okay. So our objectives for today are to understand the Poisson regression for counts and rates, to understand how to apply Kaplan Meier analysis, how to interpret Cox proportional hazard models, and also to understand what assumptions lie behind the application of these methods. So just as a form of an overview, if you remember, for linear regression, your model was a straight line, and you were your null hypothesis was was hinged on a difference in means, while for logistic regression, it was a difference in odds. Now we're going to be doing Poisson regression for count and rate, and the null hypothesis is the difference in the log of the mean and the log of the rate. This would become clearer in the coming slides. And then for the Cox proportional hazards model, it would be on your left-hand side, you would have the log of the hazards. Again, as we go ahead, we'll be able to understand what's really is going on. So for the data set that we're using today is a cohort of resident doctors who were followed up for 10 years. And from this data set, we want to identify gender differences in workload and retention. So some of the data that was collected in the data set include things like the number of calls, what is the gender, how long have they spent in residency, at what point did they exit residency, and whether or not they are still in medical practice. So just in terms of maybe how this might be used in real life terms, this can help with planning by policymakers and the government. If they know that people after this number of years would likely stop practicing medicine, then they know that for every X number of doctors that are joining the workforce, they need to plan for an attrition rate of Y%, if that makes sense. So let's just go ahead and do the Poisson regression. The Poisson regression is for count data. So if your outcome variable of interest is a count, that means a non-negative integer, then you use Poisson regression. Or if your outcome is a rate, you can also use Poisson regression. So let's say we want to know the number of call duties done by resident doctors in this data set differs between male and females. The outcome of interest is the number of calls, which means this is a count variable. And because of that, we're going to do a Poisson regression. Now, this has a few assumptions, that the dependent variable is a non-negative integer. So you cannot do -1 or -5 calls in a month, for example, and that the observations are independent, and that there is equidispersion in the dependent variable. This just means that the mean and the variance are equal. So let's go to SPSS. As you can see, my computer is from 1960, so bear with me. I'm just closing this. So I'm going to import the data. Import data. My data is in CSV format. So RDS 10Y CSV. And then OK. And we have the data set imported. So as you can see, there's different scores: mental health score, job satisfaction, workload. We just come to the variable and we'll see what the variables look like here. So if you come back to the data view, you see that there are a lot of decimal places and all that. So for the workload score, I can see that this actually is a fraction. But for everything else, okay, maybe the mental health score is also takes fraction. But in order to display it, I would just want everything to be very clean. So I'm coming to the variable view and I'm just putting the decimal places to 0. You don't have to do this. You get the same results either ways, but I prefer to look at very clean. So, okay, for the number of hours worked, this income and everything, I'll leave the one single decimal places. And coming back here, we'll see that everything looks clean and the data set doesn't look scary anymore. So that's one area. So we said that we were going to determine whether the number of calls differs between male and female resident doctors. Now we have a variable here called female, where 0 is coded as female and 1 is coded as male. So we are going to apply our our Poisson regression, because the number of calls is a count. So we come to analyze, and then we come to generalized linear models. Then again, generalized linear models. So under the type of model, we choose Poisson log linear. And then we come to response here. The dependent variable is the number of calls. So we come here and select calls. And then the predictors, we are only interested in gender at this moment. So, and gender is a categorical variable, therefore we put it in factors. So options here, category order for factors, and what it means is that if you say ascending, then it is using from 0 to 1. If you say descending, it is counting from 1 to 0. So Descending means that it is subtracting females from males, if that makes sense. It's subtracting the log mean of females from males. So we go to continue. I'm not going to change anything else here. I'm just going to go and select OK. Okay, have I done something to annoy? Apologies, let me go back again. So we go to generalized linear models. Yes. Yeah, so I don't think there's anything wrong with what I did in the first place. So we go here and then we come to the output. So the output starts from the model information. It tells you that the dependent variable is the number of calls, number of call duties taken by the residents, and it is done using a Poisson regression, and this is linked through a log function. Now, in the case processing summary, we can see that there are no missing values. And then maybe in terms of the categorical variable information, you can see that there are this. You can see basically the distribution of males to females. So when you come to the continuous variable information, you can see a summary of the dependent variable, which is the what's it called? The number of calls. Here it's not giving us the variance, but we can use this table to test the assumption of dispersion, meaning that the mean is equal to variance. So when we come to this output, we can see a lot of parameters here. But what we're interested in order to check for the equidispersion, is this deviance as well as the Pearson chi-squared. The value divided by the degree of freedom, that is this particular column, should be as close to 1 as possible for us to say that there is equidispersion. So this basically tells us that the model has failed that assumption. So this is something to keep note of. And if you were to go into your analysis to do descriptive stats on the calls variable, and you asked it to calculate your mean and variance, it will still give you different results. And that's how you would know that the equidispersion assumption has failed. So the tests of model effect here is basically testing the model without at a baseline without inputting the what's it called now? Without inputting the female category as a variable. Sorry, I'm wondering why we can't see the. So there's something wrong here. Sorry, let me go back. So the female as a factor. Continue. So, okay, sorry. So I did not go all the way to the end. When you come to the model, you would put the factor that you selected here, you'd input that into the model. So the reason why we don't have it coming here is because I forgot to send that into the model. Now, this is one of the drawbacks of point and click statistical software like SPSS, because there are things that you have to remember to do and the software is not going to do them for you. So here, I'm just going to check if there's any further things that I need to adjust. So under statistics, I would like to know the exponential parameter estimates. So this is the SPSS screen that you are looking at. Who asked that question? Let me see. Yeah, okay, Unachupu can see the screen. Yeah, Motlohi, maybe try logging out and back in again, or maybe adjusting your monitor. Okay, so under statistics, we select exponential parameter estimate. If you remember, let's go back. The reason why we're doing that is because our final answer is going to be in form of a logarithm. So we need to exponentiate it to actually get a figure that makes sense to us. So we now go back to here. In terms of the statistics, also this chi-square statistics, world versus likelihood ratio, these are just two different statistical tests that could tell you whether or not your model is or not your model is statistically significant. So we select OK, and then now I think this is our this is our generalized linear model. Everything else that we have said stands. Then when we come to our goodness of fit, we can see the value / degree of freedom is still way out of range, very much different from 1. The omnibus test tells you the significance of the model itself without imputing the variable, that's the predictor variable. The test of model effects, now this tells you the significance when you use the female variable to predict a difference in calls, to check whether there's a difference in number of calls. Now, here is our actual model. This is the Poisson regression, this table that says parameter estimates. So what are we interested in? We're interested in this particular line. Remember, female is 0. So this is female minus male. So the intercept for the log of mean number of calls taken by females as compared to male resident doctors is minus 8.0 minus 0.801. So this is the intercept, but in order to get a number that we can use, we have to exponentiate it, and this is where it comes, exponent of b. If we want to know the significance of this, we check the confidence intervals, whether it crosses 1 or not. And we are using 1 as the null value because this is a ratio. So this does not cross 1, so it's statistically significant. If we go to the p-value, it's also much less than 0.05. So our exponent of b gives us 0.449, or you can say 0.45, which is 45%. So if you want to interpret this, you can you would subtract that 0.45 from 1 to give you 55%, and that would tell you that on average the average number of calls taken by female resident doctors is 55% less than what was taken by male resident doctors. Now I'm just going to enlarge this and demonstrate this same table that we have seen on a larger screen. And then sorry, this is what I mentioned earlier about the test of equivariance. And then this is the intercept, right? Log of female calls minus male calls, and that's why you have a negative sign. And then here is the explanation. So when you exponentiate this minus 0.801, you get 0.45. Because this is less than 1, we subtract it from 1, and then we get 55%. So on average, compared to their male counterparts, female residents took 55% fewer calls. Okay. Did we get that? I'm just looking at the list to see if anyone has their hands raised. Okay, give me a thumbs up if that's all good. If you want me to take it again, also you can unmute and say that.
Sorry, Dr. Mohammed. I just joined. I was racing against time to drive in before to join the lessons. I just joined. I'm just seeing Poisson regression now for the first time. So.
Did you join the class, the main class where the theory was explained?
Oh, unfortunately, no.
Okay, so it may be a bit difficult to recap everything, but basically what we use when we use Poisson regression is when you have an outcome variable that is a count. So when if you are trying to model the number of hospital visits, number of calls, number of cardiac arrests, number of deaths, anything that is a count, then you would use Poisson regression. And that's what we have just done. We just modeled the number of calls taken compared between male and female residents. So here, because the mean itself, in terms of the difference between the groups, can take on as high a value as possible, and in order to make the value, the regression more robust to those variations, we use a log. But when you do log, you are converting difference into fraction. So that's the reason why I mentioned ratio here. So let me just go back to the output. I don't want to go all the way back to creating the table. But this is what the output of a Poisson regression looks like. Here you have the test of model effects. It tests how well your predictor variable predicts the variation in the outcome variable. And our predictor variable here is the female variable, that's gender, whether male or female. And we can see that this is statistically significant. That is fine. One of the three key assumptions of the Poisson regression is that in the outcome variable, the mean and the variance are the same. So we test this using this goodness of fit table. We look at the Pearson chi-square and deviance lines. And on this column that says value divided by degrees of freedom, we would like the value to lie between, let's say, minus 0.9 to 1.1. So as close to 1 as possible. The closer it is to 1, the better your model actually satisfies that assumption. But another way to go about it is just to do mean and variance of your outcome variable. And if you do that for the number of calls, you'd still realize that these are different. So once you are done with all of this, then you'd come to the actual regression table. Our reference category is female, which is 0. So we are subtracting male from female, and we have a negative sign here. So right out of the gate, we know that the number of calls taken by males compared to females is higher. But by what degree, by how much, we don't know. So we would exponentiate this. I did not select exponents when I created this screenshot. So let me just go back to the SPSS table. So if you look here, the exponent of this minus 0.801 is 0.449, and the confidence intervals also do not cross 1, which means that they are statistically significant, and you can see that also from the p-value. So this 0.449 or 0.45 tells you the difference between the percentage, the difference in call duties taken by male versus female residents. So because this is less than 1, we would subtract it from 1 and express it as a percentage. And that is what we have done here. So we subtracted this 0.45 from 1, now expressing it as 55%. So on average, because of this negative sign, we would say that on average, female residents took 55% fewer calls compared to male residents. I think it was Jerry that asked the question. So I don't know, does this one?
Yeah. I was the one that asked. So just one question before we proceed. The Poisson regression is considered one type of logistic regression?
No, it's not. It's not a logistic regression per se, but it's a log. You are also, so if you were here when I showed the null hypothesis of all the different regressions that we are covering in this course, you can see that apart from the linear regression, where we actually just modeling a difference in the means, so just straight up x minus a minus b, everything else is a log. So here we are modeling for the difference in the logarithm of the means, and that is the reason why we had to do an exponential. Does that answer your question? Someone asked a question on the chat box also about how the goodness of fit table affects the reading and interpretation of the final model results. So when as you look at this, you can see that even though our model is statistically significant, this assumption of equivariance is not satisfied, and it's very much wider than what we expect. So you should have it at the back of your mind that there's probably some other factors that you have not taken into consideration that could actually modify this relationship. So that 55% might actually change if you are able to identify and incorporate those factors, those predictors into your model. Alfred, does that answer your question? Yeah, okay.
Yeah, yes, thank you.
Okay. So another aspect that we can look at in the same Poisson regression is rates, the component of time. So now we are saying that women are taking less call duties than men. But what if actually men are spending, or women are spending less time in residency? And that's the reason why, they are having fewer call duties. So in that case, there is something called an offset feature, which basically adds the time variable into the regression model. So it's basically tries to minimize the effect of time in making that prediction. So not really adding time as a predictor variable, but removing that time as a confounder. And there's a feature within the regression, Poisson regression, called offset. So let's go back to our data set and do the regression again, this time around, putting the number of years spent by the resident as an offset and see what happens to the percentage. So we come again to analyze generalized linear models, type of model, Poisson log linear, that has not changed. The dependent variable has not changed. Predictor has not changed. But here we need to define the offset variable. So the number of years spent by the resident in residency, now we have put that in. Everything else remains the same. Just checking to see that, yep, these things are checked. And then we click OK. So again, the model has displayed. This is giving us a summary of the model information. There are no missing values. All cases have been included in the model. Gives you a summary of the distribution of the categories. It tells you what the dependent variable is and what the offset is. And it's telling you that for the dependent variable, all 161 members of the data set have a value for the dependent variable. So everybody has a value for number of calls as well as the number of years spent in residency. And when we come to the goodness of fit table, again, we can see how wild the numbers are running. But just for the sake of argument, let's come to the table here and see what has now happened to the value of the parameter estimates. Okay, I think something has changed because this is supposed to still be a negative value from what I did. Survive. Okay. Yeah, it has changed because the zero is what's it called? Zero is female, so it's supposed to start from 0 to 1, but it has actually done it in the reverse order. And now we have the correct sign. So it has subtracted male from females. And you can see here we have a negative value still, although the coefficient has changed. And then when we look at the exponent, we can see what it looks like, about 44%. So it hasn't changed that much, even when we consider okay. Even when we consider resident years. Now, bear with me. Apologies. There's an important step that I missed here. If you remember, we said that we are modeling everything in logarithms. So I'm actually supposed to do a transformation of this of the time variable into logarithms. So apologies for that. Let's just do that very quickly. Again, if this were R would just take that and do it automatically. So this resident years variable, I'm just going to give it a name to say resident years variable. Under the function group, under all, I'll look for natural logarithm, ln, and double click that, and then apply that to the resident years. So when I click OK, a new variable will be created. So let's go to the variable view. So a new variable has been created, which is the log of number of years spent in residency. So now when we go to our analysis, generalized linear models and okay, and click OK. So it has given us oh, sorry, I just did the same thing, calculated without putting the offset here. We have to change the offset to log of resident year, years in residency, and click OK. So now we have now we have a different coefficient, and then when you exponentiate that coefficient, you see that it's 1.15. So you would now subtract this from, you subtract 1 from this, and you'd say they actually took 15% more calls than their male counterparts. And if you look at the confidence intervals, again, it doesn't cross 1. So this value can actually take anything from less than any positive value from 0 to infinity, but from when you have it less than 1, you subtract this from 1 and then express as a percentage. When it is 1 and a decimal, you subtract 1 from it. By the time it starts to get to 2 and above, then you would just say they were twice as likely or 3 times. They took 3 times, twice, double the number of calls or triple the number of calls compared to male counterparts. Are we happy with that? Okay, let's see thumbs up. Okay, so that is rates. So when we have other types of analysis, let's say we're trying to see the time to event. So now in this data set, hypothetical data sets, residents were interviewed annually to see, to check whether they were still practicing medicine. And at every interval, they would either answer yes or no. Are you still practicing medicine or no? And then you ask, if they say no, you would record the dates and month in dates in month and year. So we have our we have our time variable recorded in months because it's month and year. Now, this particular analysis, what it does is it estimates the probability of survival over time and compares this probability across groups. It can compare this probability across groups. So there's the Kaplan-Meier curve, which visualizes that probability of survival. And there's the Cox proportional hazard model, which actually calculates the risk of the outcome, which is leaving medical practice at any given time during the follow-up period. So if we look at this story again, to answer question number 1, what is the time origin of the study? Anyone? Alfred, who's on the call? Let me just look at the Stanley.
Can I just see the question again?
Yes. So, so the question or the narrative says that in 2009, a study was conducted among resident doctors, asking them about their workload, and every year after that, you went back to the same group of doctors, asking them if they were still in medical practice, and if they were not, you would ask them when they stopped and record that data. So based on this, we want to calculate what the probability of survival was for that group. That's what's the probability that someone stayed in medical practice. And also, we would want to do that across the whole group and then between males and females. So time origin of the study, that's 2009, that's not difficult. What's the target event for this particular analysis?
Dropping out of practice.
Okay. And what do you think the time scale will be like?
Yeah, I don't know if that's...
So just think about it. We recorded the time that the person dropped out of medical practice in year and months. So what should the scale be recorded in?
Months.
Okay. Now, in the main class, there must have been some discussion about administrative censoring and other types of censoring. So Can you tell us when censoring happens in this study? Administrative censoring happens in this study. It's fine if you don't know the answer. Just nominate another person.
No, maybe I should attempt. So censoring will probably be when someone, like, you're unable to follow up someone.
Yes,
in the
but
cohort.
in particular, administrative censoring.
Oh. Would that be at the end of the study?
Yes, so that will be after 10 years.
Yeah.
But so you were actually answering a question number 5, like when would a patient be censored before the end of the study? And you mentioned if the person is unreachable. Do you have other examples?
Someone could die.
Yes, yes.
Study, yeah.
Or if they withdraw consent and they're no longer happy to be in the study. Okay, so let us go ahead and visualize the probability of survival across these 10 years in the group of resident doctors that we studied. So we're still going back to an SPSS, and so we come to our analysis. We'll come to the ribbon, come to analyze, we go to survival because we're doing a survival analysis. Then we select Kaplan Meier. So we are going to put the time here. Sorry, that's not it.
Sorry, we are not seeing your SPSS screen.
I think you might be the only one that's not. Can anyone see my screen?
Yes, I can see it.
Okay, so who complained about not seeing it now? Can you see it? Has it come up?
I'm only seeing the PowerPoint, not the SPSS.
Maybe it's taking some time to change on your end.
Okay.
So let me just stop sharing and share again and see. So can you see SPSS now?
I'm only seeing your picture.
So I think it's actually the speed of your connection. So my picture showed up a few seconds, maybe 1 second before the screen showed up, because I'm using 2 devices and I can see on the other device the SPSS screen.
It's okay.
Okay. All right. So in order to do our Kaplan Meier curve, we would come to analyze, select survival, and come to the option that says Kaplan Meier. Our time, we said we measured it in months. So this is switch months. Basically, the time in months that it took for a resident to switch careers from medicine. And then we put it in here. The status, exit, has the person exited, yes or no? Now we would, there's a question mark here in the bracket, so we'll have to define that event. It's coded 0 and 1, 1 for someone who has left medical practice. So we click, we enter 1 here and click continue. And then from here, we can click OK, and it will show us, let me see, what are the options? Yep, survival table. Okay, so we'll click on survival plots, and it will show us the Kaplan-Meier curve. And then we click continue and click OK. So it takes some time because of the number of observations in the data set. It took some time to show up. Now it has given us the case processing summary again. This is the survival table, basically showing us the individual data points at each point in time when the survival was measured, how many people were remaining. So at 10 months, 160 doctors were remaining in practice. At 12 months, 159, and so on and so forth. So this is basically what is then visualized using the Kaplan Meier curve. Now, this curve does not separate the survival probability into male and female. It just tells you that of the overall group. We're going to go back and do that again for male versus female. One thing that we usually like to, or one thing that is commonly reported along with this Kaplan-Meier curve is actually the median survival. However, for this particular group, that median was not reached. So if you can look at this axis, this vertical axis, you would see 0 to 1, which is the probability. So the probability over the 10 years of follow-up never dropped down to 50%. So there isn't a median to report. So you just report it like this. The median, the mean is not a good choice for survival data because a lot of time it is actually skewed. So you would report this graph, and in order to be able to see whether this particular what this test that you have done is statistically significant, as you are doing your survival analysis in your option, you can actually where is it? I think there's something called log rank. Okay. Okay, I think that's for when you divide it into two groups. So let's look at the survival between males and females and see how that compares. So yes, so when you are comparing the factors, you would want to see whether the difference between the two groups is actually statistically significant, and you can use this log rank test, which basically assumes that the probability remains the same across the whole time period. And for the other two tests, it actually recalculates the probability based on the number of participants that are still remaining within the data set. So if at some point, let's say you have lost 10% or 20% to follow up, and then further down the line, you have lost 5%, further down the line, you have lost 3%. So this is very good in checking for statistical significance in that scenario. This does the same thing, but the denominator is different. So we click continue, and then we click OK. So again, these are the same tables from before, but now the graph has separated into two. So it tells you that the blue line is female and the green line is male. Or have I mixed it up? Yeah. So one of them is male, one of them is female. I didn't prepare the data set, so I'm not very sure which one is which. But the one in blue basically where you have a lower line. So each drop here, each drop in the line represents a drop, someone who has actually reached that outcome of interest. So each time you see a drop, it means someone has left medical practice. And for the group that is in blue here, it means that they are dropping out at a faster rate than the group in green. So let's say the blue are men and the green are women. It means that men are actually dropping out at a faster rate than women. And if we look at it, if we want to really check that, let's say here at 60 months, this is the halfway point. If you draw a straight line upwards, you would see that the probability of survival here is less compared to is less in men compared to women. So you see the probability has actually dropped here. If you trace it to this point, it would be like, I don't know, 0.81 or 82, whereas here you'd have 0.9 probably. So that's kind of how you would interpret it. And then remember we requested a log rank test when we did the comparison. So this is the table for that. So it tells you whether this difference that you are observing, this difference in probability, is statistically significant. If we look at it, it's not. So that's the use of this table. So the Kaplan-Meier curve is very good at visualizing these differences in survival. However, it is limited because it's not really able to tell you the effects that maybe other variables might have on this survival. So, for example, even the statistical significance, we actually had to select a different test to tell us whether this difference we're observing is statistically significant or not. And another limitation is that it cannot really account for the effect of confounders. And for that, we are going to have to do what is called Cox proportional hazards model. So are we clear on this particular part? Do we understand now how to draw Kaplan-Meier curves and how to interpret? So like I said again, these drops basically represent when someone has actually told you they have dropped out of medicine. These pluses indicate a censorship event. So this plus at the end indicates the end of the study. However, pluses before then indicates that maybe some participants have dropped out either by withdrawal of consent or lost to follow up, or the participants died, or for whatever reason we are not able to reach them again. Those are the pluses that are represented here. So it's actually taking us I think we've been quite fast. Yeah, so I just brought here some screenshots of the curves that we just saw over there. So for the Cox proportional hazard model, we're modeling the risk of the event happening. So I think yeah, ran out of time before because I just prepared these slides this afternoon. So for the Cox proportional model, we are modeling the risk of that event of interest happening. So our event of interest is living medicine. So we are modeling what's the risk of living medicine between men and women. And we would come here to the same menu, survival, and would come to Cox regression. So our time variable is the same in months. The status is the same, exits, is the person there or not? And we define it as 1 for someone who has left medical practice. And then here we would input covariates using our variable female. And then we'd come here to this option that says categorical to tell SPSS that actually this is a categorical variable. And like we said, 0 is the code for females and 1 is the code for males. So we would click first and click on change. So when you select something, if I just select this and I just say continue, it's not going to change here. So if I want it to change, I would have to actually click on my selection and click change and then click continue. Once that has been done, I can come here. I can still request plots. These are the same plots over there. So it doesn't really give me that. It's going to plot the same Kaplan Meier curve if I select plot over there. But here under options, I can also select whether or not I want confidence intervals for the exponent of the coefficient. And that I have selected. Okay, everything looks good. And then we click OK. So it says Cox regression. So we're going to start interpreting from here. And then again, it's giving us a summary of the processing. And also a summary of the categorical variables. Now, again, this is just a representation of the model without our variable. Here, this particular table tells us whether or not the model itself is statistically significant. That is, whether or not adding the variable female to this model is statistically significant. And that's why it says change from previous step, the previous step being block 0. So we can see that the addition of that variable actually did not make a statistically significant change to the model, but we're just going to go ahead for the sake of interpretation. Now, this is our coefficient for the hazard ratio. And then when you exponentiate that, it gives you 0.5, so about 50%. So basically, it means that compared to women, men are living or rather, compared to men, women are 50% less likely to leave medicine, because this is negative. We're subtracting. We're subtracting 1 from 0, right? And female is 0. So it's telling us that compared to male counterparts, women are 50% less likely to leave medicine. Or if you flip it on its head and you decide to take the reciprocal of that, it means that men are leaving medicine twice as fast as women in this group. If you look at the statistical significance, it's not, and that is also reflected by the confidence interval. So this is this is the Cox regression, and if you have additional variables that you want to impute into the model, you would go to the same option and you would just impute additional variables in here, and you'd be able to tell. For example, where is the job satisfaction score? So let's impute job satisfaction score and keep everything else constant and say okay. And now we can see that we can see the effects that job satisfaction score has on the likelihood to leave medicine. Now, if you want, this model also has some assumptions. And the assumption, one of the key assumptions is that the probability for that hazard ratio remains constant across the whole duration of follow-up. And you can test that assumption using something called, I think it's a Schofield test. In this set of options, it's actually represented by this log minus log plot. So for the for this categorical variable, you would want to impute it into this box that says separate lines for. And then what we want really is for the lines to remain separate throughout the graph. And that would really tell us that, okay, this assumption has been met. So if you look at it here and click OK, so we can see that the lines have actually met in some, the lines have met here and they have met here. And it's also supported by our other model where it says that it's not statistically, actually they are two different things. But yes, because they are meeting here, it means that the assumptions are not the assumption of the constant probability across the across the time point is not met, and you can then maybe move on to some other tests that would help you to better understand the relationship. How are we doing so far? Any questions? Does anyone want to give us a short recap? Should I ask my questions? Who was unmuted? You wanted to say something?
I wanted to ask about this last curve.
Mm-hmm.
Is it the same curve we've been working on, and like how did we transform it this way.
That's Alfred, right?
Yeah.
Yeah. So this is not the Kaplan-Meier curve. This
All
is a log minus log curve.
All right.
Is a visual representation of Schofield test. Can I type somewhere? So it's basically testing one of the assumptions of the Cox model. To make it very simple, when we draw this curve, we want the lines to remain separate.
Okay.
So if they meet, it means that the assumption has actually not been met. And then we would actually not report this, or we would have to make some adjustments before reporting it.
All right. Thank you.
Yeah. Anyone else? Okay, I think we have actually, this is the first time we're covering the material in such record time, but we have gone through the things, the models that we said we were going to discuss, which is the Poisson, Kaplan-Meier, and the Cox proportional hazard models, as well as talking about the assumptions for the individual tests. So what I would like us to do is to get data sets, get sample data sets. You can get sample data sets from kaggle.com, K-A-G-G, sorry, I'm belching, kaggle.com, and you can even get sample health data. Or if you have live data from a study that you've done, you can also use it to practice everything that we've done so far in SPSS and even more. So we have only scratched the surface of what is possible with SPSS. We have basically curated some of the most commonly relevant statistical tests for the kind of studies that we commonly do. However, if there's anything that's you are trying to achieve inside of SPSS that was not covered inside here, this is just to give you a springboard. You can always Google or check for videos on YouTube or even ask AI. Just ensure that you fact check whatever it is you are getting from AI though. So there are also very nice and simplified books on statistics that you can consult, something like Medical Statistics at a Glance, and several introductory texts that would really help for a deeper understanding of what we have covered in this course. So at this point in time, if there are no further questions or comments, I would like to thank everyone for attending all our sessions. This is going to be the last SPSS session, and wish you a very happy new year.
Sorry, are we getting the slides of yesterday and today?
Yesterday should be available on the classroom. These slides for today, I will share with Dr. Abioye for any edits before they are uploaded to the classroom. Because I just made these ones this afternoon, so they will have to go through editorial process before being uploaded.
Okay, thank you.
Yeah, you're welcome.
Thank you very much, Yisa.
Thank you very much.
You're welcome.
Thank you so much.
Thank you for joining